In this video, we're going to take a look at projectile motion, which is our first use of two-dimensional vectors to describe motion. Specifically, we're going to look at the concepts behind it, what governs both the horizontal and the vertical motion, and what kind of general things we can say so that we can kind of predict what the motion will be and answer questions conceptually, even if we don't fully have the math written down. So the first scenario to consider that kind of leads us into this discussion, if you imagine throwing a ball straight up in the air and then catching it, or you imagine throwing a ball in an arc. So we've got sort of crudely drawn A and B. And you might say, well, which one will be in the air for a longer time? Which one has a greater initial velocity? And what factor actually determines the time in the air? So we'll revisit this when we get together next time. But I want you to maybe pause the video, jot down an answer to these questions that you can then revisit at the end of this video. Sometimes what we do is we use a device that can both drop and launch a projectile at the same time to visualize what's going to happen here. And so if we look at this, we might predict which one will hit the ground first, the one that's launched or the one that's dropped. And then you might ask, well, what if it went really, really fast, the launched one? Would that make any difference to the answer to this question? In general, we think of this in this way. This is a very common photo that you'll see of a sort of high-speed camera shot of a ball being launched horizontally and one being dropped. And you'll notice that each frame, which is each picture of the ball, is at the same time interval. And every time you go the same amount of time, you also go the same amount of distance down while one moves horizontally. So there's something really interesting going on there. And the fundamental idea with this is that the horizontal and the vertical direction of motion can be completely separated from each other. We can look at the vertical motion and we can look at the horizontal motion, and then we can combine them together. So what we're going to do, this is on pages 39 and 40 in your packet, is kind of look at how this actually functions for an object. So here's our kind of grid, a very simplified version of what we just looked at. And we have free fall in object 1, and 2 is horizontal projectile motion. Now we can go ahead and track the motion of an object using some software to kind of figure this out, which we will do. But then we can also, now that we've learned how to track that and sort of see what happens, we can predict what will happen in each of these scenarios. If you have this as your starting point and you know that it is a horizontal velocity, then we should only have horizontal motion that goes at a constant velocity because there's nothing slowing it down or speeding up. Notice the horizontal separations are all equal in equal amounts of time. On the other hand, in the vertical direction, right, we fall further each second. This is essentially overlaying our free fall that we looked at in a previous video on top of this grid. And if you combine the X position at a given time and the Y position at a given time and kind of connect those dots, you find out where the ball would be as a projectile. So projectile motion is nothing more than horizontal constant velocity motion combined with vertical free fall motion. And so if we use that information, we can lay on top of this a lot of useful information. We can start by thinking about, well, in the X direction, what has to be true? Well, there's constant velocity. So that means the position is just rate times time. Right? In the Y direction, it's constant acceleration, so all of our free fall kinematics equations should apply. So X final is the Vx times t, and Vx is equal to a constant. In the Y direction, the final Y position is the initial Y position plus the initial Y velocity times time plus 1/2 gt squared. The only real difference between this and what we saw before is that the equations now have a few extra subscripts, and we're using y's instead of x's here because we're talking about separate dimensions of motion. We can do this in the velocity space. The final y velocity is the initial y velocity plus g times t. And the equation that doesn't involve time still works as well. So if we put all this information together, we should be able to actually track the velocity of a projectile. And this is a great simulation to play around with what happens if you sort of change the angle. You can fire things horizontally, you can do all sorts of stuff. Let's look at this video of a ball rolling across the table and then becoming a horizontal projectile. I've already gone through and tracked the video to sort of see what happens as it goes through. As you can probably see, as we click through, you see a little dot appearing. So I've already done the work to find out where the ball is in any given moment as it flies through the air as a projectile. I've also set the scale. This is 1 meter here, and the origin. So the X is the horizontal direction, positive X is to the right, and positive Y is up. So we've kind of done all of that. And I can turn on tracking of this and go ahead and see it. And this is the path it takes, right? So once we have that information, there's a lot of things we could do. Certainly, the software is capable of generating some graphs for us. And these graphs I have put in are the position time graph for both the X and the Y position, and the velocity time graph for the X and Y velocity. And so if you look at the X position, it is a straight line, right? If I, select this data, a region of it, and I say, well, what is my curve fit that I can do here? I'm just going to do a linear curve fit. Of course, the red line has a nice curve fit, but the other line does not. And so that's really kind of what we're looking at. One of them is a straight line, one of them is not. And the curved one is the Y velocity because it's accelerating, or the Y information. Down on the bottom graph, we have our X velocity, which is essentially constant, and our Y velocity, which was 0 until it left the table, and then it got faster, and we see it accelerating in the negative direction. Now we can do a few more things with this. We can go ahead and sort of watch the whole thing happen as we go, right? Generate these graphs. Or we can take a look at the vectors at each point. And I'm just going to look at velocity vectors. I sort of put them all on here, and that's a lot to see. But as you can see, the velocity vector, there's a component in the X and a component in the Y. And the whole total velocity is changing as it moves through, getting faster and faster. So if we actually turn off this trail to see everything, and we kind of jump back to the beginning, we can step through this until I start tracking it. Notice as we're rolling across the table, we essentially have a constant horizontal velocity to the right, the X direction. And then as it leaves the table, we start getting a Y component of velocity. And the further we go, the bigger the Y component, while the X stays constant, and the total velocity keeps getting bigger and bigger, and also a much more extreme angle as we travel. Now it's off the screen here, so you can't really see it, but that's the basic idea. And so this is what we want to do in tracking a projectile. But if we were to think about, what if instead of launching a horizontal projectile, we actually launch a projectile at an angle? Well, the big difference is that we've given it an initial velocity that was non-zero in the Y direction as well as in the X. The same rules apply. We still have constant velocity in the X direction, accelerated motion in the Y direction, but we now have an initial condition that's a little bit different, right? If this is a 50 meter per second velocity at an angle of 53.1, Mr. Graham's favorite right triangle, the 345, says that the initial X velocity is 30 meters per second. And since that is a constant, it will be 30 meters per second for all of the various times, 0, 2, 4, 6, and 8 seconds. In the Y direction, 345 right triangle says we have an initial velocity of 40 meters per second up. And since we are accelerated due to gravity, every 2 seconds we change our speed or our velocity by negative 20 meters per second. So after 4 seconds, we're at the top. And then after 8 seconds, we're back down negative 20 and negative 40 meters per second. We can use the Pythagorean theorem to fill out all the middle column, but we'll get to that. But we know that our x position starts at 0 at the ground. And if we plug into our simple x motion with constant velocity, we get 60 meters after 2 seconds, 120 after 4, 180 after 6, and 240 after 8. In the y direction, we have acceleration. So we start at 0 meters, then we go up to 60 meters after 2 seconds, then we go up to 80 meters, and then we come back down in a nice symmetrical pattern, just like free fall. We can then plot those values on our graph in position, which we have there. And then we say, well, if this is the shape of the position graph that shows where the object is, we can also start to think about, well, what is the velocity for each of these points? And I am going to have to cut out some stuff. There we go. So we can trace the path, which is sort of what we would expect from a projectile. We can go a little bit further and start to say, well, what is happening with the velocity at each of those points? Well, we've got 36 meters per second, using the Pythagorean theorem, at 2 seconds, then 30 meters per second at the top because we have only x velocity, 36 again, and then 50. So the last thing to do would be to add some information about velocity to this graph. Right? We can draw in the x components of the velocity as all being 30 meters per second. And the y components of the velocity start upward, are 0 at the top, and then go downward. And then we can draw in the total velocity, which is just the sum of the x and y as vectors, which looks something like that. You can do some additional reading on vectors in Chapter 3, Sections 1 through 7, and we'll do some conceptual practice problems when we get together in class.